which is nothing but the open circuit voltage, which means if I remove this load resistance from these two terminals, and if I measure the open circuit voltage between these two terminals, so I can have a voltage source which is equal to the open circuit voltage in these terminals, and that will be in series with the Thevenin's resistance, and this Thevenin's resistance will be nothing but, if I can open circuit this RL, so let's say I remove this RL, and if I see here what is the internal resistance from this side, from this end, if I can see the internal resistance, so that will be sources, and I will open circuit. So two terminal bilateral linear DC circuits, it can be replaced by an equivalent circuit consisting of a voltage source in series with the resistance. Now a circuit will be given to you that will in that we'll have a load resistance, and now we are going to replace this circuit with the Thevenin's equivalent circuit, which will have a voltage source in series with the resistance. Let's say this is my X terminal and this is my Y terminal, and this will be that resistance RL. Now let me illustrate this with the help of a small example. So you can note it as problem number 16. Now you can consider the simple DC circuit which I am going to show here. This is my load resistance RL, and let's say this is the current IL that is flowing through the load resistance, and this is resistance R3, R1, and let's say this is the source Vs. And now you have to find IL using Thevenin's theorem. You need to find this current IL that is flowing through this load resistance using Thevenin's theorem. Now, when you use Thevenin's theorem, what you have to do is you need to replace this much part of the circuit. Okay. So this part of the circuit within the dotted line has to be replaced with a voltage source in series with the resistance, and that voltage will be nothing but the open circuited voltage at this terminal, the load terminal, and RTH will be nothing but the resistance when we actually see from this load terminal. Let me get into the details of this problem. Now, first of all, let me find the open circuit voltage. So this is nothing but when you actually remove RL. Now in the previous circuit, when I remove RL, how will my circuit look like? When I remove RL, my circuit will look like this. So this will be my R1, this will be R3, and this will be R2. Now I need to find the open circuited voltage at this terminal, So that open circuit voltage will give me the Thevenin's voltage, that is VOC or VTH. Now, using this voltage divided rule or current divided rule, so you'll be able to very easily find out the open circuit voltage at this particular terminal. So how to do this? So the voltage between these two terminals, now if you see here, how to find the voltage across this resistance R3, let's say you consider a loop current I. So this will be nothing but I times R3, and what will be this I? So this current I that is flowing through this resistance R3 will be nothing but voltage Vs divided by this current R1 plus R3, because current won't be flowing here because I have actually open circuited this terminal. So if you listen carefully, I have open circuited this terminal, so therefore the current won't be flowing through this path. So ultimately the current I will be nothing but this voltage V divided by the total resistance R1 plus R3. Now this will be nothing but the open circuit voltage that I get here. Fine, we have found the first part, and the second part will be I need to find the resistance that will be connected in series with this V open circuit. Now how to do that? So to do that, you will have to actually short circuit the voltage sources, and you need to open circuit the current sources. So short circuit the voltage sources or open circuit the current sources. So this indirectly means you are actually replacing those sources with their internal resistance. So I have put before you that the voltage source will have an internal resistance in series with this, and current source will have an internal resistance in parallel to it. So what we are basically doing is we are trying to replace the voltage source and current source with their internal resistances, but here there is no internal resistances that that has been given or that we are considering. So ultimately we are actually just short circuiting this voltage source, and if at all we find a current source, we will just open circuit it in the process of finding RTH. Now when I do so, when I open circuit that voltage source, I will have R1 here, and I will have R3, and then R2. So this is the terminals across which the load was connected. Now I am looking from this terminal and trying to find the resistance. So what is this resistance in total? We have R2, then we have two resistances in parallel. Summing up these two, we will get actually the RTH. So R2 and then R1 parallel R3. So yes. So RTH is nothing but R2 plus R1 parallel R3. So how to find the parallel combination of these two resistances? The equivalent resistance will be R1 R3 divided by R1 plus R3. Now this will be your RTH. And now the given circuit can be replaced by this open circuit voltage that we have computed in series with RTH, and then we will have the load resistance, that is RL. And now this becomes very easy for you to answer the given question, that is to find IL, which is nothing but the current flowing through the load. Now how to find IL? IL will be nothing but the open circuit voltage divided by what? RTH. If you look at this loop, so there is one voltage source and two resistances that are in series. So therefore the total resistance will be RTH plus RL. Now this will give you the current that is flowing through the load. So this is a simple illustration of your Thevenin's theorem. So if you compare this circuit with the circuit given in the question, so I have replaced that except the load, the remaining part of the circuit, I have replaced it by a voltage source in series with the resistance. Now, in the same way, if you go to Norton's theorem, in Norton's theorem, we will be replacing it with the current source in parallel with the resistance. Fine, that we will look at later on, if not today, and then in the next class. Let us try to solve a problem. Before that, let me see if there are any questions. If not, I will go to the problem. You can take it as problem number 17. Find the current through 10 ohm resistor using Thevenin's theorem. The given circuit is, you have a 10 volt source here, then in series with that you have a 2 ohm resistance, and then in this branch we have 5 ohm series with, say this is again the 10 ohm resistance. So you need to ultimately find the current that is flowing through this 10 ohm resistance, which means that except this 10 ohm resistance, the remaining part of the circuit should be replaced by a by Thevenin's network. That is, we need to have this VTH, that is nothing but the open circuit voltage across these terminals, in series with RTH. So when that is done, we will be able to see what is the current that is flowing through this 10 ohm resistance. And here we have 20 watt. Fine. So this is 1 ohm, 10 ohm, 5 ohm, 12 volt, 2 ohm, and 10 volt. Fine. So what are the two things that need to be found? We need to find the open circuit voltage across these terminals, and we should also find the equivalent resistance, the resistance that is RTH when we actually look from this terminal. So let us go step by step. So as a first step, you need to remove the 10 ohm resistance in order to find the open circuit voltage across the terminal. So in that way your circuit will look like this is 2 ohm, this is 10 volt, 5 ohm, 12 volt. Now I have actually open circuited these terminals, removed 10 ohm. So this will be a 1 ohm resistance. It's the 20 volt. So this is the voltage that we need to find out. And this voltage is same as what? So if you look at this terminals, open circuited terminals, and this are in parallel. This 5 ohm resistance and this 12 volt source are in parallel. Okay. So ultimately, the voltage at this node A, voltage at this node A, and voltage at this particular point is same. So I hope you will agree with this. The voltage at this point and this point are same because we don't have anything in between. So let's try to find the voltage at node A using nodal analysis. So at node A, if you apply the nodal analysis technique, let us say node A is at a higher potential than all other nodes. So therefore current will be flowing from this node to other nodes. So in this branch, the current that is flowing will be VA minus 10 divided by 2 plus in this branch it will be VA, and if you look at this polarity, this is minus and plus, so therefore it is VA minus of minus 12, so that is VA plus 12 divided by 5, and if you analyze this branch it will be VA minus 20 divided by the 1 ohm resistance, so this will be 0. Now when you simplify this equation, you will be getting will be minus 5 plus 12 by 5 minus 20. This is equal to 0. So you must be getting around VA is equal to 13.29 volt, and this is nothing but my open circuited voltage in this particular terminal. So ultimately I have found this terminus voltage, that is VOC, that is 13.29 volt, because once I remove this particular resistance, if you see here, the voltage at this point of the circuit and this point of the circuit will be same, and that will be nothing but the voltage at this node A, which I have found out using nodal analysis technique. Now what I need to do next is I need to find the Thevenin's resistance to find RTH. To find RTH, what I must do, if at all there is a voltage source, I must short circuit, and if at all there is a current source, then I must be open circuiting it. Now once that is done, what will happen to the previous circuit? So when I short circuit the 10 volt voltage source, I have short circuited the 10 volt voltage source, and then we have the 5 ohm resistance, and here again there is a voltage source. I have short circuited that, and then I have this 1 ohm resistance. Fine. So I have this 1 ohm resistance, and here there is again a voltage source. I have short circuited this. Now ultimately I am interested to find what will be the resistance when I actually look at from this particular point. Now ultimately you will see that there are three resistances that are actually connected in parallel. So this is similar to this 2 ohm resistance, 5 ohm resistance and this 1 ohm resistance. They are connected in parallel. Now this will be my RTH. So what will be RTH ultimately? So this will be these three resistances in parallel. Let's say when you try to find the parallel combination of these two, this will be 2 into 5 by 2 plus 5. You'll be getting something, and this is in parallel with this 1 ohm resistance. So what will you get? This is 10 divided by 7 parallel 1. So this will be 10 by 7 into 1, 10 by 7 plus 1. So you must be getting around 10 by 17, yeah. So therefore the given circuit can be replaced by the open circuit voltage that we have computed. That will be 13.29 volts. So we have computed the open circuit voltage, and RTH will be 10 by 17 ohm. So this will be RTH, and then we will have the 10 ohm resistance, which we actually removed from the circuit to begin with. And now what am I interested in? I am interested in finding the current that is flowing through the 10 ohm resistance. So how to find this current? So this current IL will be nothing but the voltage whatever we have here. So that is 13.29 divided by 10 by 17 plus 10. So if you calculate, you will be getting around 1.26 ampere. So this will be the current that is flowing through this 10 ohm resistance. Let me see if there are any questions. Okay. So if there are no further questions, that we can go to the next problem. Now, the same technique what I have shown here also applies when we have dependent current source and voltage sources. In this circuit, I have shown a problem with only independent voltage sources or current sources. Now, same thing can be also applied for circuits that are having independent current sources and voltage sources. So such type of problems I will deal with later on. So in today's class we will focus on only independent voltage sources and current sources. Now that brings me to the next problem. Problem number 18. Obtain the Thevenin's equivalent circuit across the XY terminals, and take down the circuit which I am drawing. So these are the XY terminals. You need to find the Thevenin's equivalent circuit across this XY terminals, which means that the entire circuit that you see here in the left hand side of this XY terminal has to be replaced by the voltage source, that is open circuit voltage, in series with the Thevenin's equivalent resistance RTH. Okay. So let us proceed step by step. Now, first of all, if I want to find the open circuit voltage, let's say it's already open circuit. Change the color. So whatever I am going to write in green is actually part of the solution. Now here, so you need to find the open, it's already open circuited. So what will be the open circuit voltage? So that needs to be examined, and it becomes very easy to find the VOC if you know what is the voltage across these terminals. So let's say, let me mark this as A, B, C, D, and if you can find the voltage across these terminals, then it becomes very easy for you to find VOC, because ultimately this voltage added up with this 5 volt will actually give you this VOC. Now, to make this possible, what I can do, I can apply Kirchhoff's voltage law in this particular loop. I can assume a loop current I, and if I can find the Kirchhoff's voltage law in this particular loop, it will be easy for me to find VCD. Fine. Now, what will be the voltage across this terminals A and B? Now, you see from here, now the same voltage, 9 volt, it also appears across this 9 ohm resistance. So, and the same voltage also appears here. So, ultimately here also you will have this 9 volt. So, same, because it's actually these three are in parallel. So, ultimately here also you will have this 9 volt. Now, when I write this apply Kirchhoff's voltage law in the loop A, B, C and D, I will be getting let's say here also, let's say you have the 9 volt. Fine. So when you travel along the direction of this current, so here you are having a voltage rise and plus minus and then plus minus. Now only at this particular place there is a voltage rise, and all other places there is a voltage drop if you go in this direction of this current. So you have 9 volt, let's say, in one side, and in the other side you have, let's say, all the voltage drop, that is 2 times this I, then plus this drop 3 volt, and then here it is 2 times I, and then here you have 10 volt. Now from this it is very easy to find I. So this is 4I plus 13. Now what will you get? 4I is equal to minus 4. Therefore I is equal to minus 1 ampere. Now when you know I, you will be able to find VCD, isn't it? Now when you know I, it will be easy to find VCD, because it is ultimately this 10 minus whatever may be the drop across this resistance. So that will be your voltage across the terminals, VCD. So is nothing but 10. So what will be the voltage drop here? 2 into the current I is minus 1 minus 2. So that will give you 8 volt. So ultimately the open circuited voltage that you have here will be 8 minus 5, 8 minus of minus 5. So this will be ultimately 8 plus 5 will be getting 13 volt. So this voltage is 8 volt, and here you have already a 5 volt, and 8 plus 5 will get 13. So that will be nothing but the open circuited voltage. Now we need to find the Thevenin's equivalent resistance. Now to do this, what we need to do, we need to actually open circuit the current sources, and we need to short circuit the voltage sources. When I do so, the circuit that I have given will get reduced as follows. Now here initially there was a voltage source. It will take you back to the circuit. So what am I going to do? I am going to short circuit this 9 volt source, and here it will be an open circuit. So ultimately there will be no current that is flowing here, because I am going to open circuit this portion, and this will be short circuited, and this will be short circuited. Fine. And now when I short circuit this, what will happen? When I short circuit this, you see here current always flows through a low resistance path. Let's say you have a path with a 9 ohm resistance, and you have another path which has, let's say, absolutely no resistance. So obviously the current will be flow through the low resistance path, which is this short circuit. So ultimately this there will be no current that is flowing through this 9 ohm resistance because we have shorted it. This is 9 ohm. And here we have this 3 ohm resistance. So this is open circuited, so no path here for the current. And this is the 2 ohm resistance. This is again another 2 ohm. And the voltage source that was in series with this is short circuited. And similarly, this is the 3 ohm resistance, and again the voltage source that was here was short circuited. This is the X and Y terminals. You need to find what will be the equivalent resistance when you actually see from this particular terminal. So what is it actually? So this will get this has been short circuited, so this is will be actually eliminated from the circuit. So ultimately we have three ohm, 2 ohm, 2 ohm. So this RTH will be nothing but 3 ohm plus 2 ohm parallel 2 ohm. So that is 3 plus 2 into 2 divided by 2 plus 2. So that will be what? So this will be around 4 ohm. Now ultimately the Thevenin's equivalent circuit that you are looking for, this will be the open circuit voltage that you have computed, that will be 13 watt in series with this resistance that you have calculated, that will be 4 ohm. This will be your X and Y terminals. Now what is the use of this theorem? Let's say you have a load, any load you are connecting to a circuit, and you are not at all interested in what happens in the other part of the circuit, whatever this let's say this is an internal circuit of any device. Fine. So we are not interested in what actually happens in this part of the circuit. I am only interested in how much current that is flowing through the load. So by using this Thevenin's equivalent circuit, I will be able to reduce this entire circuit. Now this is very complex. I will be able to reduce this to a open circuit voltage in series with RTH, so therefore my analysis becomes much simple. Let me see if there are any questions. Yeah, so there are no questions, so therefore I will go to the next topic. Norton's theorem. Now, just like we replace that complex circuit with the open circuit voltage in series with RTH, now here in the Thevenin's equivalent circuit, we will be replacing that with the current source, which will be nothing but the short circuited current in series with the internal resistance, which will be nothing but RTH in this case, but this will be in parallel with this current source. And this portion of the circuit which we will be obtaining will be nothing but the Norton's equivalent of the source network. Now this becomes, when I obtain this equivalent circuit, it becomes easy for me to analyze what will be the current that is flowing through this particular source IL. Now let's say we can whenever you replace this RL by any other resistance, let's say you are plugging in this source to supply any other load. Now in that case only RL will change, none of this is going to change. So therefore this equivalent circuit that you once obtained can be helpful in many other ways when you actually plug in a different load to this particular source. Now again let us take a so this is the problem number 19. Just to help you to understand the Norton theorem in a mathematical way, let me say I have a circuit like this, Vs, very similar to what we had previously, R1, R3 and R2, it's the same circuit, and we have RL. Now what I am going to do, I am going to replace this portion of the circuit with the Norton's equivalent, that is a current source in parallel with the resistance. And after doing that, I want to find what will be the current that is flowing here, that is IL. Now how to do this? So first step, in the earlier case I removed this load resistance, that is in the case of Thevenin's equivalent circuit. What I did to begin with, I removed this load resistance and I found out the open circuited voltage in this terminals. Here what I am going to do, I am going to short circuit this terminals. Fine, I am going to short circuit, I have to remove the load and then short circuit this terminals. So that will give me the short circuited current. This will be R1, this will be R3 and R2. As I told, I am going to short circuit this load terminals. Fine. So that will give me the short circuited current that is flowing through this load terminal. Fine. And that is one important thing that I am looking for, that is ISC, that is a short circuited current. So now if you use the current division rule, it will be very easy to for you to find the short circuited current, because there will be some current that will be coming out of this source Vs. Okay, let's say this is the current I, and this current I gets divided here through this R3 resistance, and another portion flows through this R2 resistance, which will be same as the short circuited current. The current that is flowing through R2 will be same as this short circuited current ISC. So therefore, using current division, first of all, if you want to find this I, how to find this I? This I will be nothing but this voltage Vs divided by the equivalent resistance. Equivalent resistance in the sense we have this R1 plus R2 parallel R3. So we have R2 and R3 in parallel. If you add that with this R1, we get this resistance of the remaining part of the circuit except this voltage source. So that Vs divided by R1 plus R2 parallel R3. So that will be Vs divided by R1 plus R2 R3 divided by R2 plus R3. Now I know I is already known to me in the previous step. So from I, how will I get ISC? I can use the current division rule. So that will be nothing but the total current I into the other branch current, the current that is flowing through the other branch, that is so the current, total current into the other branch current, that is R3 divided by the total current. So that will give me the current that is flowing through the short circuited terminals. Total current into R3 divided by R2 plus R3. And the next step that I need to do is to find RTH. To find RTH, what we need to do, just as we did in the previous case, you have to open circuit the current sources and we need to short circuit the voltage sources. So once that is done in the circuit, we'll have only one voltage source, that Vs. So that I have short circuited, and then I have R1, R3 and R2. So this has been already short circuited. Now what am I interested in? I am interested in the resistance when I actually look from this terminal. So this will be my R in, that is RTH. So in this case, sorry, not RTH. So it's a Thevenin's, this is Norton's theorem. So therefore it is wrong to use this notation RTH. So let us stick with R internal resistance. Internal resistance of this source network. That's what it means, R int. To find this R int is nothing but R2 plus we have R1 in parallel with R3. So that is R2 plus R1 R3 divided by R1 plus R3, that will be R int. Now once that is done, the given circuit can be replaced by a current source which is equal to the short circuit current, and now these are the terminals across which RL was connected. So I have obtained the part of the circuit that is inside this dotted line is nothing but the Norton's equivalent of the source network. So let us solve some more problems related to Thevenin's and Norton's theorem in the upcoming classes. So now it's already time up. You can leave the meeting if you don't have any questions. You can